Audible?
Yes.
All right, cool. Let's get started.
Hi everyone, I'm Deepak Sarda. I'm the product lead for chaos engineering within JPMorgans Platform Services Group. That's the group that builds and operates our private cloud platform. And
I'm Garima. I am the engineering lead for chaos engineering framework we have at JP. And we will be taking you through our adventures of chaos engineering in the firm, along with our lovely little hamsters that we have created our own army of hamsters that cause chaos. All right, okay, let's get started then. Start off, the talk is based on experience that we've gathered practicing and evangelizing chaos engineering inside JP. So the opinions have been formed over a period of time, and they are not the opinions of JPMorgan Chase. Okay. So what we'll be covering today would be what is chaos engineering. So a little bit of theory. Then we'll get into action. We'll actually do chaos engineering in this room. And then we will talk about how did we scale chaos engineering for a firm of our size. And we'll look into the size as well. Okay, so an intelligent person somewhere in the world said storytelling is a great way of inducing ideas, putting ideas out there in the world. And as a mother of a 3-year-old, I would absolutely agree on that. So on 21st April 2011, Amazon was carrying out a normal network change, which was for their EBS service, which is the elastic block storage that they have primarily for their EC2. And what ended up happening was there was an outage in AWS US East region. So the network change they had was a very simple network change. In the primary network that they had one router, and they planned to switch the traffic to another router in the primary network so that they can do some upgrades. And what ended up happening was the network change went bad, and rather than switching to the other router in the primary network, they switched to a router in a redundant network, which was not built to scale for that kind of traffic that EBS normally gets. And hence there was an outage in AWS East region. So what happened in the outage? EBS service, which is built primarily for EC2, was rendered not usable. So you cannot read, you cannot write, and as an effect, there was massive outages on people consuming the service as well. Now, guess why this outage happened? Any guesses? Okay. It was a configuration error, just someone's accident. But what ended up happening was a lot of things were rendered not usable. So if anyone has looked into Amazon's shared responsibility model that they put out for the AWS services, what they do in that model is they say, okay, so these are the service offering and platform offering that we have, and this is our responsibility. And for the incredible reliability AWS services provide us, they clearly state that reliability and engineering of all our services and making sure that they are up and available is in our hands, but the resiliency of your application is in your hands. And you need to build resilient applications leveraging our amazing and incredible platform that we offer. But despite that clear contract that they share with their users, with clear SLOs and SLAs stated, there was massive ripples across the web. And some of really popular websites were impacted. I've put in a couple of icons that you can relate to. That's Foursquare, Reddit, Quora, Heroku. There were a lot of those impacted. But in this impact, one ship sailed through. So there was one company which continued to service its customer despite their heavy reliability on the service, and they were not impacted. Any guesses on that? Yes. So people who were using Netflix were doing Netflix and chill. They were not impacted. They were not impacted. And why did this happen? So let's look at that. So the reason this happened is they were well prepared. They're quite well prepared. They had made their whole design cloud native, highly resilient services and applications in that model. So they had stateless servers, stateless services, they had redundancy built in, they had backups, caching, all those goodies that you talk about, they had that already. So they were well prepared. But more than being well prepared because they built resiliency in, they were well prepared because of one more reason. Because they were prepared for failures. So this, if you remember on the first slide and on this slide as well, this outage happened on 21st April 2011. And they were using Chaos Monkey back in 2010. So they had a Chaos Monkey running, which was killing their services at random points in the day, random services, and their developers and their ops had to be ready for that kind of failure. So they were ready for failure. They were getting their whole workforce ready for such events, making sure that there's enough observability built in so they can find these more proactively. And their customers were not impacted. But did they stop there? No, they learned more from this. So Chaos Monkey typically goes and randomly kills services at random times in their production environment. But this was a whole AZ outage. So what ended up happening was US East region EBS was not available. And they had not really done an AZ outage before this. So they realized, okay, we clearly were not impacted, but we had some degradation of service offering. So maybe we can do better. So the business KPIs were impacted, not that we saw that impact, but let's say the number of clicks per minute that they tracked were low. So they said, okay, what can we do? Let's build Chaos Gorilla. It's going to go kill the whole AZs. So they built Chaos Gorilla, which started going and killing AZs. And then I think they didn't stop there. They have other monkeys. They have Janitor Monkey. They have Conformity Monkey. And they built CHAP. They have a lot of such tools added to their toolkit. I think the more important thing is the world learned over and over from these mistakes. And hence came chaos engineering. So chaos engineering is a practice that's primarily put out there, so which allows you to be ready for failure. So it's a industry standard now. It helps you be ready for failures, and it helps you also build resilient applications. So you just don't assume I've built resiliency in. You actually test them. You put them out for testing. And there's not one or two companies using it. There's a massive list of companies that's adopted these practices, and they're continuously doing this. So there's some icons we put out here which you will relate to. JPMorgan Chase. Yes, so there are a lot of companies practicing chaos engineering, and they're contributing to the open source toolkits that are out there so that the community overall can grow. With that, let's now take a deeper dive into what chaos engineering is. So let's understand chaos engineering. I have very nicely swiped this definition from the internet. Swipe was a word taught to me by some other female mentor I had, which means steal with intelligence, pride, and excellence. Chaos engineering is the discipline of experimenting on distributed systems in order to build confidence of your system's capability to withstand turbulent conditions in production. On first glance, it just looks like a normal definition. But then we would like to highlight a couple of words here. Discipline. So while the name says chaos, it's not chaotic. It's a very methodical approach. It's structured, and we'll see in the practice session on how you approach it. It's about distributed systems. So while you can leverage chaos engineering for any complex and monolith systems that you have, we are primarily concerned with the distributed systems. With microservice architectures, dynamic scaling cloud environments, CI/CD pipelines, agile kind of working environment, your ability to make changes and scale them has massively increased. And hence, the places where failures can happen have massively increased. Hence, distributed systems are an interesting study for chaos engineering. Production. Because the real environment is production, the real users are in production, and when the actual impact will happen, it will be in production. So production is an important keyword here. There's a lot of literature actually. Back on this slide, you'll see chaos principles of chaos engineering website, really quick read, highly encourage people who are interested, who are already practicing or want to start practicing to read. There's a lot of good literature available by some of the leading sites who've put together white papers, case studies, how they have learned RCAs out there. I would really recommend for those who are either practicing chaos engineering or want to start, should leverage this literature to make their practices better and better. So I'm going to go and emphasize on a couple of things. Chaos engineering is about breaking things. So you break things, you break them again, and you break them again, and you break them again, until they work again and again and again. But chaos engineering is not chaotic, and that's a very important point I would like to emphasize before I move to practice. Okay, so let's practice chaos engineering. Our muscle man here is ready, and let's get into some action. So I said chaos engineering is very systematic and methodical. So for the demo that we'll be doing and the way we'll be developing our practice, we will be looking at a very simple application. It's a greetings application, just says hello world along with the container details it is running in, and we've deployed it on 2 Kubernetes nodes that will be running on my system, and we load balance them with worker1.local URL out there. Just pretty straightforward application. And this pattern that you see here is pretty commonly referred as a hot architecture design pattern or active architecture design pattern, because it helps your application to be resilient to failure of let's say one AZ or one cluster or one node, hence leads to high availability. Okay, so what do you first do? You understand the steady state of your system, which means what do you expect your system to be in a normal circumstance? What's the threshold? Minimum response time, maximum response time, how many, example Netflix says how many persons have clicked the button in a particular time period. So those kind of steady state behaviors you come up with. Then you say, okay, this is my steady state behavior in a normal circumstance. What is the acceptable variance in an experimental circumstance? And hence you form your hypothesis. So for the application you saw in the previous page, let's see the hypothesis. If a Kubernetes node is experiencing an outage, then the greeting service should not be impacted. Straightforward? Okay, so now we have a hypothesis. Let's experiment. So in the typical science terminology, once you have an hypothesis, you want to be able to experiment, because experiment is what helps you invalidate or validate a hypothesis. So from our college days or our school days, a hypothesis is not like a proved thing. You over a period of time develop confidence in it, or you are able to invalidate it with one experiment, right? So it's just one experiment that needs to invalidate it. And for a given hypothesis, there could be many experiments. So let's look at one of them. I can just stop the Kubernetes node that I have, and the service should not be impacted. Straightforward. Which would look like this. So I have taken my hello world service Kubernetes node, and I said, go just drain that node, shut it down or drain it, right? Or I can stop all the services running in the Kubernetes node. So I just manually go and terminate the process, or if it's like kill and give the PID, etc. So that could be another way of doing it, which would look like that. Now both those experiments look similar, but there are differences, and this is something that we've learned with an actual experience inside JP. In the first case, what ends up happening is it's like a crash. It's gone. There's no trace of it. And GLB actually took roughly a couple of seconds to identify it's gone, and there was an actual impact. And before chaos engineering, when people were doing this, what was ended up happening was they were gracefully shutting down their stuff. So it was deregistering from the load balancer, and there was no impact. So there was no impact, but when they did like, let's just kill it, there was an actual impact. So hence, by just creating different experiments, which may look similar, but there's a different approach, it changes the way you look. And these are just 2 of those examples. There are many of those out there. Okay, so now that you have experiments, you want to run them. You want to try them out. So you do trials, right? And trials are how I would say a runtime instantiation of an experiment, because every time you do the same thing, the situation would have changed. 9 o'clock in the morning on my website, there might be massive traffic because people are traveling, they're leveraging my application to do some shopping. Maybe at 10 o'clock, not so much. So the time, everything depends, right? So that's what turns into kiosk trials. Example, you want to first test it in the test environment, gain a little bit of confidence. Then you want to do it in production, maybe in the off-peak hours, so you've not impacted massive customers, and then you realize no impact. Let me try it off in peak hours and see I have no customer impact, and so on and so forth. So you can come up with more such circumstances. What if I inject heavy load? What if I do it over a weekend, etc. So let's do a demo of this. Okay, so is that visible to everybody? All good? Okay. So let me just put a quick watch on my Kubernetes nodes, and you would notice there's a master out there and there are 2 worker nodes. Okay. And now let me just clear my screen and let me just do this. I'll delete my pods to start off with. Okay, and I have a clean slate, and Kubernetes will spin them back up. Thank you. So you would see one of the pod is running on worker 1 and one of the pod is running on worker 2. Okay, so I'm going to put a watch on this as well, so you can see both the workers are running. Now let me take you quickly to the experiment we have. So as I talked about steady state hypothesis, you would see in the steady state hypothesis, and this is for the demo and we've kept it simple, but you can go ahead and measure against Prometheus and other monitoring tools, even your business KPIs out there. But this is a simple HTTP probe where I'm probing the URL. Actually, before I probe the URL, I will quickly go here, clear my screen, and do a curl on this guy. Okay, so this one, if you see, is returning the same hello deployment number as one of the workers. If I hit it, you will see it's returning the other one. So it's just round robin between the 2. Okay. All right, so let's go back. So here we've done a steady state, in the steady state hypothesis, we've done the HTTP probe, and we're checking if the response time is 200. Okay, and then let's go to the actual injection of chaos, which you see in the method area, and you'll see we are doing a drain nodes. So what drain node does, it removes all the workers running in that nodes, and it makes sure no further workload can be run on that, right? Okay. So that's drain node. And once I'm satisfied with my experiment, irrespective of whether it failed or passed, I want to make sure I can restore the system. So I'm going to allow the next pods to continue getting installed back on the worker node. Okay, so let's run the chaos experiment. Sorry. So it's validating syntax. Yeah. So you would see what it has done is it's running a steady state hypothesis, application respond, then it's doing the action of draining the node. So it's draining the node. After draining the node, it checks again the application is running. And for those who would have noticed while the experiment was running, and I can run it again, you would have seen one node was terminating and the worker was put in a non-available mode. Let me run that again quickly. Yeah, you can see the age of the pod as well. But if you see, okay, just too quick. All right, but yeah, so the termination happens, the worker is unavailable, and still all our HTTP probes throughout went green. So that's what we are able to prove, that we did build the experiment in a way that application in a way that it was resilient to that particular failure, right? Now, if I would have not had the 2 replica set and I would have gone ahead and deleted it, the HTTP health check would have failed. Okay, so again, just a fan of making sure I'm recapping the most important things. We said we want to go through the steady state first. We need to understand the steady state first. we need to focus on creating a hypothesis. We run our experiment. Very importantly, we observe our system. If I would have run the same experiment without HTTP probe, I really didn't know how my experiment reacted. So there was no learning, there was nothing out of it. And then I learned something about my system, right? If it's a passing thing, great, but if it's a failure, that's even better because I've learned and I can solve that and not let that happen in an actual production environment. And there's another key important difference I want to highlight here. A lot of time people say chaos testing, chaos experimentation, resiliency testing, and sometimes we have to use those words for people who are new to it to get them accustomed. But more importantly, there's a major difference here. Experimentation leads to new things, while testing is just validation of assumption. And that's the key factor that we encourage people to understand when they're following chaos engineering. And with that, I'm going to hand over to Deepak, who's going to talk about how we applied it to a scale like ours and the scale. Yes.
All right, thanks, Garima. I hope you enjoyed the demo. That was just a small flavor of what chaos engineering is like. And the first time we started showing these kinds of things in our company, obviously people were a bit worried because we keep repeating the word production, 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 and no one wants to be the one who goes and breaks production. Like, who wants to be the one who breaks production, right? So obviously, when you're introducing something new to a new kind of practice to your company, there's going to be pushback, there's going to be folks who don't get it. And a way to bring them along. You need a way to change how your company approaches things. So based on our experiences doing this at JPMorgan, we wanted to share what we did with the hopes that you'll be able to take some of this and apply it in your own companies as well. Just a quick note on what JPMorgan does, right? I've been in this company for about 6 years now, worked in 2 different. Even to this day, the scale of the place just continues to surprise me. For example, in the commercial bank side, we move $6 trillion in payment every single day through our systems. Half of the US households, whether they are digital or using credit cards, they bank with JPMorgan using either our website. And so that kind of business scale is what drives our technology strategy. We spend about $11 billion in technology every year. A good 1/3 of that is actually net new investments in new technology initiatives. We employ more than about 50,000 technologists. And all of this is just to drive that business, right? So I'm showing these numbers not just to say, JPMorgan is awesome, which it is, but I'm also showing it because that's the scale of this company. And so obviously introducing something like chaos engineering was not going to be an overnight exercise, a walk in the park, right? So how did we do it? Thankfully, we didn't have to start from scratch. What I mean by that is JPMorgan actually cares very deeply about resiliency of its systems. Having downtime is not good for us. If our payment systems are down even for an hour, that causes a major disruption bluntly to the world economy because we move so much money through our pipes, right? So anything that helps us improve the resiliency of our systems, we would invest in it. And so chaos engineering, right? So how did we go about building a chaos culture at JPMorgan? First, we started by building some tooling. This tooling allows our application development teams to practice chaos engineering safely and do it in such a way that we have clear visibility into our risk and controls and audit systems. So we have a good understanding of what's happening, who introduced the chaos, why did they introduce it, what was the outcome, and what did we learn from it, right? Actually, this tooling is the bulk of the engineering output from my team. Garima is the engineering lead of the chaos engine that we built. The next thing we did with the tooling in place was to create guided paths or paved ways for our engineering teams to adopt chaos engineering. So we created tutorials, we created patterns, we created safe environments where they could practice chaos engineering, gave them examples of how they would create chaos experiments for the different types of resiliency scenarios that their application needs to meet. So we created these paved waves. Building on top of these, we created internal communities around chaos. So in these communities, we brought together engineering teams, we brought together SRE and operations team, we brought together our risk and controls teams. And this is really important. You have to create this community because no matter what someone else outside of your company tells you, it's your community which can be unique to your company, and that's only through a community, right? And all of this is, of course, trying to get to that place where chaos engineering is part of your everyday culture of your company's development practices. The way I think about culture in the context of chaos engineering is to how automated testing is. So today, automated testing is a very core part of our development practices. It's just like, it's unimaginable to say that, yeah, we have a code base which has no automated tests. That's just not a thing. But if you move back about 15, 20 years, it was a very different landscape. In 1999, automated testing was sort of an outlier. JUnit was written in 1997. Ken Beck's XP book came out in 1999. So it took quite a long time for automated testing to become part of our culture. And so our chaos engineering is kind of at that place. There are a few success stories. There are a few companies adopting it, but we have a long way to go, both in terms of broadening its use, but also improving how we practice this discipline. So there's a lot to cover in all of these. It will become, I think, 4 talks if we did all of this. So in today's talk, we'll just focus on that paved ways. How do you create a safe path for your engineering teams to go from, hey, what is this chaos engineering thing, all the way to running their experiment in production? So this is the paved path that we created for our engineering teams. Everything from educating them about what is chaos engineering, all the way to getting their first experiment running in production. So we'll break this down one step at a time. First, we created lots of tutorials, just very step-by-step methodical guidance for engineers to take and go and run chaos experiments. So this would be everything from simple hello world chaos experiments like the type Garima showed you, where you just crash containers in Kubernetes, to very sophisticated experiments where you're introducing very targeted latency between microservices, for example, and see what would be the impact of that. And we created these primers so that folks could, in a very self-service manner, follow along and start practicing in their environment. But if you read these tutorials, and you may be worried to go and try it on your actual application. So we created sandbox environments, playgrounds for our developers to go and practice this safely without actually impacting their day-to-day system. So these sandbox environments, they come in, they run chaos experiments, we just wipe out the environment and restart for the next developer. And then, so these are what we think of as self-paced learning, your documentation, your sandbox environments. But we complemented these self-paced learning environments with more active learning environments. So we created internal meetups, we created workshops, and just kind of got people to come together and learn chaos engineering. Okay, so people find out about chaos engineering, they get excited, they follow the tutorials, do some sandbox exercises, then they say, we are ready. Where do we start? What's the first chaos experiment we should do? And our response to that question is summarized in this slide. Maybe you're familiar with this slide. This is the 4 quadrants of awareness and understanding. So you've got your known knowns on the top left, all the way to unknown unknowns on the bottom right. So if you apply this to resiliency of your systems, on the top left are the resiliency characteristics of your systems, which you know of, which you understand very well, and you know exactly what will happen, right? So again, the demo that Garima did, that's a very well-known behavior of your system, that because it's load balanced, if one side goes down, I know the service availability will still be there because I've got another node, another data center, another AZ taking care of that load. So that's a very well-known property of your system. So that's known knowns. You look at known unknowns. Known unknowns are those things where you know what this is, but you don't know what would be the impact on your system, right? A good example of this is circuit breakers. How many of you are familiar with circuit breakers as a microservice design pattern? A few hands. So I'll just do a quick recap of what is a circuit breaker. So in microservices, you have two services communicating with each other. Service A makes a network call to service B. Occasionally, that network call may be slow, either because there's a link breakage or service B is actually overwhelmed with lots of traffic, so it's slow in serving responses. So service A could just keep retrying, but that doesn't help because just by the act of retrying again and again, you actually put more load on service B, and because now service B is even more overloaded, its performance keeps deteriorating. So a circuit breaker is a pattern where in between these two services, you introduce, from the electrical engineering terms, put a circuit breaker where if the service B is having problems, you don't call them, you just time out, and then after some time, so that you just kind of trip a circuit. Okay, so a lot of folks, when they implement microservices, they follow the standard best practice. If you're using Spring Boot, it's like one annotation, add circuit breaker, happy days, right? But do you really understand if the circuit breaker will work in production? Because have you actually brought down the other service and see what would be the response? There's so many variables that go into a circuit breaker that you understand what is happening, but unless you actually do it in production, you wouldn't know what would be the response of your system. So you have to go into production, trip the circuit breaker, and see what happens. So that's a known unknown. Unknown knowns are interesting. These are actually environmental, system environment things which you understand, but you had no idea they would impact your system. Like these are kind of surprising things. An example of this is daylight saving times, right? Like we don't have it in Singapore, thankfully, but there are parts of the world which are still in the 14th century and they like to switch their clock twice a year back and forth. So you know this happens, but how many of you know exactly what happens to your system when that clock shifts by an hour? You have no idea, right? And probably till I brought this up, you wouldn't have even thought about that. So that's an example of an unknown known. And so you have to do it to find out how would your system respond. And finally, we get to the really scary bit, which is the unknown unknowns. When it comes to unknown unknowns, there's obviously a question, right? I don't know what this is, so how will I even start thinking about this? And so for this, our advice is just to keep an open mind. What you can do is look at other incident reports, look at postmortems, look at RCAs from other systems, and then see just think what would happen to your own system if similar conditions happened in your system, right? Based on that, create a chaos experiment, run it, and see what happens. That's how you would learn from it. Another example is to kind of invite people from other teams who have no idea about the internals of your system and encourage them to design chaos experiments for your system, because they would bring a very different perspective which you would lack. And that's another way to uncover unknown unknowns. In chaos engineering, this is the box you want to get to ultimately, because this is where you get new learning. Going back to Garima's example of differentiating between chaos testing and chaos experimentation, on the top left is when you are doing chaos testing. You know exactly what the behavior will be, you're just validating that assumption. On the bottom right is where you are uncovering new behaviors about your system. That's where the learning comes in, and that's chaos experimentation in its fullest form. That's where you need to be. So going back to that question that teams ask us, what should be our first chaos experiment? We tell them go in this order. Don't jump here when you haven't even done the first part. So go in this order, and as you go in this order, you are actually building confidence in your system day by day. Right. Production. We keep telling go do chaos experiment in production, but that does not mean you start in production. I highly encourage you not to do that, right? I don't want to be the one who you blame when you get paged because you broke production on day one because, hey, I went to this talk about chaos engineering and I'm all excited. Start in a lower environment, start in your dev environment, start in your test environment, learn things over there. Even these lower environments will teach you new things about your system. And as you build confidence, move up the chain, right? That's the key thing in chaos experimentation, building confidence by running more and more experiments, and doesn't matter where you're running those experiments. Yes, in production eventually, but you'll still get value by running it in lower environments. Interestingly enough, having this guidance as an explicit call out in our paved ways increases the comfort level with the engineering teams who are adopting chaos engineering. It's okay to start in a lower environment. That's actually where you should start. So it gives them a much easier ramp up to start adopting chaos engineering, as opposed to this whole, must do it in production, then everyone just steps back and says, not for me. Okay, fourth point. This is where everything is treated as code. You have heard of things like infrastructure as code. You have heard of things like config as code, monitoring and security as code. We say that you should also treat your chaos experimentation as code, right? In the demo that you saw, the chaos experiment was actually described in a JSON. That's a JSON that you could version control, you could check in, you could get peer reviewed, but then building on all of that, because you have a tooling that can read that JSON, you can automate your experiments. That's a big value, because once you've automated your experiments, you don't have to run them manually, you can just run them again and again on a schedule. So we have teams which, when they first start running chaos experiments production, they actually start doing it on weekends. So they just schedule the chaos experiments to run a couple of times every weekend. When nothing is happening, then they move up and say, now we are going to schedule the chaos experiments to run during low traffic hours. And that's how they start building confidence. Again, you don't have to come over the weekend to do it, just schedule it, it'll do its job. The other thing is to include chaos experiments as part of your CI/CD pipelines. Now think about it, right? In our CI/CD pipelines, we do so much of automated testing. We do unit testing, functional testing, integration testing, performance testing. But what is testing the resiliency of your application? How are you confident that a change that you made did not impact the resiliency of your system? How do you know that this release did not change the resiliency behavior and it's going to cause downtime? Well, the good news is, because your chaos experiment is now codified, you could put that same chaos experiment in your pipeline, and now you have a battery of resiliency tests that's continuously validating your system. And if those resiliency tests fail, you don't do a release. Just like if performance tests are failing, you don't do a release. That's the big power of treating chaos experiments as code. And finally, we get to production. So why production? I mean, we keep touching on this. The real reason why you want to do this in production is because there is no other environment like production. As much as we try to create copy environments, performance environments, et cetera, they will always be cheap knockoff products. It's not production, right? So you want to do this in the real thing, because that's where you'll actually learn how your system behaves. That's where the real user traffic is. That's where you can actually measure the impact on your business KPIs, which is why you need to move to production. So once you get to that place where all your engineering are continuously doing testing and running chaos experiments in production, learning from those chaos experiments, that's when you have got to this place where you have built a culture of chaos in your company. Okay. There's one more idea we want to introduce before we wrap it up, and that is the idea of observability. Observability is a long, fancy word, but it's kind of simple. The definition of chaos engineering is that you look at the steady state of your system, introduce a failure, or change the introduce some failure in your environment, and then observe the response on your steady state, right? What is steady state? There's so many variables that go into defining a steady state for your system. It could be everything from requests per second to what is the latency of your system to business metrics, et cetera, et cetera. So that word steady state encompasses so much behind it, and how do you actually measure it and report on it? That's kind of what observability is. Just building a very deep understanding of your system at runtime using telemetry. So observability is a big topic. Again, another talk. But the key thing over here is observability. If you don't know what your system is doing, then there's no point doing chaos engineering, because it's actually then just chaos. You have no idea. The failure that you introduce, what is the impact it's having on your system? with that, we want to leave you with some key takeaways for this.
Yes, I'm a big fan of takeaways and recaps. So, hello. Yes. So I think just reiterating, chaos engineering is not chaotic. So it's not unmonitored. It's not causing outages in production. It is, as we've learned through the point, it's very thought through. It's very methodical. It has a whole culture building behind it. We intend to learn from failures, be it our failures, be it others' failures. If you just like go to Amazon blogs or Netflix blogs or any blogs of these well-known sites, they have such amazing RCAs where they've written what went wrong, why did it go wrong, what could have they done differently, what will they do differently to avoid it in future. Hence, we highly encourage when RCAs are out, you should go ahead and read them. They're like extremely useful. Is it better if it fails while you watch? It is better if it fails while you're watching. So yeah, of course, you can fix it then. And yes, you should do chaos engineering production. Cool. Questions?
I have a question. So you said that in your experiment which you showed, you just had shut down one node. In chaos engineering, do you also cover when you shut down everything? I know it will not work, but but I'm just.
That's kind of true. So we've not covered it completely here, but we call it as soft chaos versus hard chaos. Actually, there are two parts to that answer. So there's something called as soft chaos versus hard chaos, where hard chaos is platform causing chaos in your environment, and your application should be built resilient to it. So example, let's say Amazon says every now and then we will do whole data center evictions for maybe upgrades, or maybe for the containers you have. If older version of Linux are getting outdated, we'll make sure we're removing them every now and then. So for those kind of things, platform does is hard chaos.
Yes.
Now you would never go ahead and kill everything unless you know what the impact is if it's your application itself. So if you have a steady state and you know that you will be able to switch to a DR environment extremely quickly under your SLA, why not?
And so everything is kind of a broad word, because you could have situations where, especially in complex enterprises, where you have lots of systems that depend on each other, you could happens if this particular system is completely down. What would be the scope of impact? And as it happens, complex enterprises, it's actually sometimes very hard to map the relationships between different systems. So occasionally the only way to find out what actually depends on something is to actually shut it off.
So of course you can build experiments only since you're the one writing the experiments. It's built on what you think can happen, right? So right now it's just, shutting down systems or something like that. So did it happen that something chaotic happened that you didn't experiment on? Basically, I was wondering how can you make experiments based on the unknowns?
So when something breaks and it wasn't a chaos experiment, that's just a production incident, right? But there's value in production incidents because they have given you learning, and hopefully you have done a good postmortem, you have done a good RCA, and you have a culture within your company where you share these postmortems widely so that other teams can learn from that. And then the next stage would be other teams look at those postmortems and say, what would happen to our system? Let's create a hypothesis around that. Let's create a chaos experiment. So that's kind of the value in those incidents.
And just to mention an analogy on that, right? When you find a bug in your code, you usually go ahead and first write a unit test around it, which failed, and then you make it pass. So it's similar.
So one way to enhance resiliency is, I guess, to build a redundant architecture, right? So what I'm not able to appreciate is this chaos engineering. Is this something complementary to that approach, or how does it work in relation to redundancy?
It's absolutely complementary. Chaos engineering is not something that is giving resiliency to your system. It's just validating your resiliency posture. It's only proving that it's actually resilient. So when you say we have a very resilient architecture, we have redundancy in all of these components, how do you know that redundancy will actually work when something breaks? So a good example of that is, so this actually happened. Garima, I think, touched on it a little bit. So there was a team which was load balancing their services across 2 data centers with the idea that even if there was an outage in one data center, their client would not be impacted because the load balancer would send the traffic to the other data center. So that's an extreme form of resiliency, right? Everything is run as a replica, active in 2 data centers. Turns out that the load balancer, when one of the data centers is cut off, the load balancer takes a few minutes to flip over to the other data center. That few minutes exceeded their SLA. So, and they had no idea it would take this long. So then they had to change their architecture to do client-side load balancing instead of server-side load balancing. Because they actually ran a chaos experiment where they shut down everything in one data center and then saw what happened from their client's perspective.
Nowadays, in the cybersecurity world, people are also talking about being prepared for failures, and no one is immune from data breaches or hacking. What do you think, or in your experience, how does security resilience from security perspective is integrated into your chaos engineering and practices?
I think that's an extremely important branch of chaos engineering as well. And in fact, recently we went to a conference where we were discussing with this chap from another company, I'm not allowed to say a lot here, but which is developing a product specifically targeting that audience as well. This area has not been explored that much. So while people have started taking their couple of first steps toward this area, it's not something that has been completely explored. In fact, Netflix conformity monkey slightly falls in that category. So where what they do is they have certain set of rules, and the conformity monkey goes ahead and causes that chaos and checks whether those rules are met or not. So I would say it's very a new area in the chaos engineering world, which has very limited tooling yet, but it has to expand. And also from Deepak's slides, if you notice those circles, there was this community that we had. In JPMorgan, security is extremely important. That's why the disclaimer slide. And hence, we have to partner with a lot of internal firm teams to take care of such things. And one of our partnership is with the security line of business, where we work with them to see how can we start introducing some of these. We are ourselves quite early in that category.
And this is kind of going back to my comment around chaos engineering today being like automated testing was 15 years ago. There's so much more ground to cover.